So as I said, my name is Junel Solis, and I'm an image data analyst here in Turku BioImaging, which is part of the Finnish advanced microscopy node of Euro-BioImaging. I just want to mention here that we have node partners across different universities here in Finland, which all together form the Finnish advanced microscopy node. And what I wanted to show you today was a little, well, not so small, but a project that we are currently working on and developing. But it focuses on handling questions and solving problems surrounding whole slide image data. So here I have some example screenshots of these tissue sections from human cerebellum, which are fluorescent stained whole slide images. And the main goal of this particular project was to measure the colocalization between the fluorescent channels targeting two different proteins. So one particular challenge that is almost the first thing that we encounter when we deal with this kind of data is the proprietary image format. So in and of itself, it's not a problem, but I have found that if you want to do with that initial image data, you want to analyze it, but at the same time, you want to visualize it and you want an effective way to store it. We found here in our unit that it's hard for one format or these proprietary formats to do all things at once. So we have embraced using OMISAR, the next generation file format, because it allows us to kind of we use this and we can visualize our data with it. We can proceed with our mostly Python-based image analysis on this kind of data, and it also fits into our data management plans of how we're going to store this data for the long term and curate it and publish it. So one thing here that I want to show you, the table on the left side, the table on the left side shows the original file sizes of some of the example slides, and they're quite small compared to when you do the conversion to OMISAR, which really quite bloats the size. There are some reasons for it, which I will not get into now, but one thing you might also notice is that the file count of these chunked file formats becomes very big. Here, they're relatively small in the low thousands and below 10,000, but it can very, very easily go into the hundreds of thousands of files. And this, when you get into this situation, this becomes a really big issue because just transferring this amount of data with hundreds of thousands of files is very slow, and it causes problems for file systems, even high-performance compute clusters. So currently, I know that there's some things going on in our bioimaging community about fixing these issues. I think with some recent releases of some libraries that have just occurred earlier this year will probably solve these problems. But this is something that we always need to be aware of when we work with large whole slide image data. Next. Yes. So over here, the first step that we needed to do was to draw the tissue boundaries. And this is not so difficult to do when you have a small image, but when you have a whole slide image that spans potentially hundreds of thousands of pixels in X and Y, it becomes very computationally expensive to calculate where are the boundaries of that tissue. And in this sense, our switch to using OMISAR allowed us to choose a lower resolution and then calculate the tissue mask from that. As you can see here in green, it shows where the tissue is, the boundary of the tissue, and just eroded a little bit. However, storing these tissue masks is very expensive if we store it as an image. So we have taken some cues from the geosciences and geography and used their image formats and considered our whole slide image to be like a map. And then we used a format called GeoJSON to store essentially the tissue boundaries, not as an image, but coordinates of polygons. And this, for one slide, instead of costing, potentially gigabytes, it will just be 1,500 kilobytes, for example, in a text file. Another issue with these slides that we have encountered is in the different fluorescent channels. You can see there in this particular one, it's quite bad. So there are a lot of imaging artifacts. So before we do any automated analysis here, we have to somehow exclude these areas. So once again, okay, so here you can see a thresholding-based approach calculated per channel that in the red shows you all the polygons of areas of the slide that are to be excluded from being analyzed because they're too bright. They're artifacts. And again, we don't store these as images anymore. We simply store them as polygon coordinates with very small file sizes. Then, because the targets of this study are intracellular, some intracellular and transmembrane proteins, first we wanted to compare the channel information only in areas that are within a fixed radius of nuclei. So that meant that we had to detect all the nuclei in the entire whole slide image. So detecting nuclei is not is quite easy if you have a small image, but when you're dealing with the whole slide image, eventually you will need to process these in smaller chunks, block by block, and then rearrange the puzzle together. So here we used CellPose and asked it to make the predictions block by block, so that we end up with so something like this to something like this, where the nuclei are detected. In this case, it's not all the nuclei that are shown here. But I hope, yeah, you get the idea. So the circles are also a fixed radius around the nuclei. This is really interesting because the circles, the white circles that you see, are also not raster images. They're just point coordinates, X and Y, the centroid of the nucleus, and you store that into a text file. And then you just say, well, there's the centroid. And then if you want to visualize it, draw a circle that is 120 pixels in radius from that from that center point. And of course here, because we have already figured out the exclusion for the image artifacts, you can see that in this particular example images, there are no nuclei, the white circles, around the image artifacts, right? And this is all up to this point completely automatic. And of course, here you can see in one part that the nuclei are also not are also a certain distance away from the tissue section border. Right. So now, as I mentioned, the nuclei is stored as point coordinates in X and Y, and over here we have also drawn, or you may also notice that there are some nuclei that are left out. And we did this in such a way for the purpose of the study that we don't want the same circle patch to be analyzed twice. So because we know the point coordinates, we could feed this into a quite fast algorithm that will find nuclei that are touching each other, like, for example, this one, and then delete one of them, exclude one of them from being analyzed. And here, of course, from these point coordinates, we can then take the patches and then make any colocalization analysis that we need to do, and then extrapolate this to the whole slide image. Now, everything that I have shown you up to this point is one slide, right? But then, and that is already a lot of compute power that needs to happen. It can take hours to process that one slide on a workstation in the office. And here in this particular case, we had high tens of slides that needed to be processed. So of course, we need a way to iterate over our image processing, iterate over it also effectively, and then use any high performance compute resources that we have. Luckily, at least in Finland, we are able to access this quite freely because we are part of the Finnish research. We are a Finnish research institution, and also for our collaborators. But in this case, I wanted to show you that here we borrow from Nextflow, which is originally intended for bioinformatics, but we just use it to do our image processing. And you can see here like a flow diagram of how the data goes. from getting the exclusion boundaries, the tissue boundaries, nuclei labels, filtering things, and then adding thresholds for how many patches or sampling percentage of how many nuclei we're going to get from the slide, and then output the data this way. For us, in the last year or so, this has really changed the game because it allows us to very easily iterate over large amounts of data without twiddling our thumbs for hours on end or even days. So we can leave this to run on our compute clusters, and this particular flow takes 13 hours to run currently with several GPUs. But that doesn't matter because then we can leave and do other things in the meantime. Yeah, so this is the team that we have here in Turku, and a lot of them also are involved in Euro-BioImaging activities and local activities, education and training and coordination. We just recently added 2 members to our team who are focused entirely on image data analysis. So this tells you that this activity is growing in Finland and I think also across Europe. I would like to invite anyone, everyone here to join us for the Bioimage Informatics Finland Network Symposium that is happening on the 22nd, 23rd May in Saili Island, which is an interesting place in the Turku archipelago. So if you have the chance to do so, please feel very welcome, and I hope that I can see you there. I think we have already invited some speakers from the Nordics, and there are also people already signed up to join this event across Europe.